I will start my talk. So just some brief introduction to myself. I'm Shan from University of Liverpool. I'm leading a robotics lab called Smart Lab. It's called Smart Lab because we have smart people in the lab. Just kidding. So it stands for Swarms, Multi-Agents, and Robot Technology and Learning Lab. And it's part of the Center for Autonomous System Technology in University of Liverpool. And today I will talk about Visuo-Tactile robotic perception. I will share my insight into the fields, and also I will share our state-of-the-art research in the lab. So here is an overview of my talk. So firstly, I will talk about the inspirations from human tasks. So I will compare the human perception action loop and also robot perception action loop, what we need for this loop, okay? And then I will talk about tactile sensors for robotic perception. So like with humans, we use the sensors to get the data. And then I will, next I will talk about how we use the data from tactile sensors for robotic tactile perception. And as the last, I will talk about our latest research on Visuo-Tactile robotic perception. So first, let's get some inspirations from us, from humans. So on the left, you can see if you are in the chemistry lab, so what we do to do a chemistry experiment, so we use our hands and our eyes to coordinate our motions. So we pick up some tubes and we see the liquid in the tube using our eyes. But also we are using our hands to perceive the weight and other properties of the tube. And then we, according to this information from vision and touch sensing, so we can adjust our pose to adjust the pose of the tube, right? So we can make the chemistry experiments. On the right, you can see we have these KUKA mobile robots moving in a chemistry lab as well. So it's quite similar to what we do in the chemistry lab as humans. As you can see, we can the robot can move around in the environments, and it can pick up objects from the stacks, and also it can transport these objects. So by comparing these two scenarios, one is human operator, one is robot chemist. So you can see both scenarios we use vision, tactile sensing, proprioception to observe the environment. But if you think about these two different scenarios, we humans always make use multimodal information, vision, tactile sensing, and other information together to do the action, to perceive the world. But for robots, usually we rely on vision, because for this KUKA robot, we only have vision as a tip of the inner factor of the robot arm. It doesn't have touch. So that's why for this video, you can see we only have hard-coded environment. If we change anything in the environment, we have to adjust its motions, or we have to adjust our code, okay? So we still like the tactile sensing for robotics. So that's why we have this workshop, and we gather the people who work on tactile sensing to facilitate the perception action loops. For sure, when we have vision, tactile sensing, we have perception. So we interpret the data from vision and tactile sensing, and then we facilitate the actions. So like picking up tubes, and also facilitate the interaction with the environment. And also in this process, definitely we have control how to adjust our motions. And also we have communication with different robots or with human operators. So for today, we will focus on vision, tactile sensing, and also movements, that is proprioception, so the movement of the body parts. And also we apply them for perception, action, interaction, and control. So first, what can we use? So for vision, we always have cameras as the robot's eyes. But what can we make use of for robotic tactile perception? So first, here's an inspiration. So that's what we usually do. So for a warehouse environment, so you can see we have mobile robots picking up objects and moving this object to another table. And from this video, you can see there are cameras as the in the factor of the robot arm, and it will help the robot to perceive the locations of the objects and also properties of the objects. Actually, it's acting as a tactile sense. But usually, the vision can be occluded by its own arm or the light, and also it can be affected by the light conditions. So currently, most of the robot platforms, they don't have the tactile sense. So if we have the tactile sense, we can facilitate these movements, these actions better. So here's a comparison of vision and touch sensing. So for vision, usually we have a large field of view. We can have a global view of the environment. And but for tactile, we usually focus on one part of the environment. So for example, the place in contact with the robot. So that is local. And in this sense, we have very rich information from visual, but for touch, we have very sparse information from this context. And for computation, so we have, so for complexity for visions, because we have this image, we can get the features, but for tactile, we have to process, and so it may be complex. But for computation, it's very high for vision because of the sparse data of tactile, so it can be low computation. And also we have to tackle these invariants in the environment, so such as scaling, rotation, translation, and illumination for vision. Also, we have some noise in tactile, so we also have rotation and translation of objects. But also, we have this illumination. So, for example, if we press harder, so the values will be higher, right? So we call it tactile illumination, right? And what sensors we can use for robotic perception? So here's a glance of tactile sensors we can make use of. So from left to right, you can see the resolution of sensors is from low to high. Okay, actually, this is high density. So for the first one, so you can see is like biometric whiskers. So in nature, we have these whiskers for these animals. Also, we can have single contact for robots as well. So by using vibrations, so we can detect the single contacts. So in the middle, we can see we have fingertip. So for fingertip, we have high resolution tactile sensing. So for human figure, we have 14 by 14 receptors for our fingertip. So we have made a lot of efforts into making these high resolution tactile sensors. So for example, from WISE, we have 14 by 6 sensing elements, and also for biotech, so distributed on the fingertip. And also we have this large area tactile sensors that can be distributed to large area body parts. So for example, our hands, arms, and backs. So these ones, they are sparse, and it can help us to detect the context. So there are researchers working on these large area tactile sensors. One good example is here from Gordon's research group. I believe Gordon will give you more details in his talk. And for my research, I focus on using these high resolution tactile sensors for robotic perception. And we have a group of tactile sensors called camera-based tactile sensors. From the name, you can see we use cameras. So we use vision to act the tactile sense. So there are two main families for camera-based tactile sensors. One is GelSight, one is GelTip. So for GelSight, we have one camera at the base, and we have a silicon on the top. And once the silicon is pressed, the camera can capture the deformation of the silicon. So then we can get imprints of the silicon. So we call it tactile image. Similarly, for GelTip, so we have a camera at the base, and we have a silicon cap on the top. So once the cap is pressed, the camera can also capture the deformations of the silicon. But instead, they are using these markers. So you can see these dots, these white dots. They only track these white dots to monitor the motions of the silicon, and then you can infer like textures or shapes of the objects that is interacting with the sensor. So in our research lab, so we have extending these tactile sensors. So we have this GelTip sensor, and for the last slide, you can see for these two type of sensors. So we only have a limited area of contacts for GelSight and for GelTip, but for we humans, for our fingertip, we not only have the tactile sense for the top, but also we have the tactile sense for the back. So we propose this tactile sensor called GelTip sensor. So we have all around tactile sensing. We use a tube for the body of the tactile sensor, and we put a camera as the base of the tactile sensor. So the camera can capture the deformation of the silicon surrounding this fingertip shape. Okay, and on the right you can see as we move this GelTip sensor at different poses, so we can detect the contact at any place of this sensor body. So here is an example how we apply this all-around tactile sensing for in-clutter environments. So for example, we have several tubes on the table. So we need to detect this collision of these blocks. So no matter is at the front or is at the back of the sensor. So by having our tactile sensor, we can detect the collision anywhere. So it can facilitate the manipulation and grasping tasks in robotics. And for more details of this sensor, you can go to Daniel's. So this work is done by one of my PhD students, Daniel, and you can go to his website for more details. So now we have the tactile sensors. How can we make use of tactile sensors for perception? So firstly, we can make use of tactile sensors for shape recognition. So we need to represent these shapes either in handcrafted features or deep learning features. So first of all, we have made some attempts to represent the tactile images in handcrafted features. For example, like shift-like features using the gradients in the tactile image. And then we can represent each tactile image into these features. So we have local tactile features. But also we can incorporate these local features with the movement of the sensor so that we can have a global picture of the object. So for example, we have a pair of scissors here. We can contact this pair of scissors for multiple contacts. For each contact, we have one tactile patch, we have one tactile image. And after multiple contacts, we can gather them together, and we can incorporate them in one 4-dimensional space. So for each tactile image, we have this local feature, and we take them as extra dimension of the 3D point cloud, because for this tactile patch, they are distributed in the 3D space. So we attend the local features to the 3D locations. So then we have this 4-dimensional space. So we can have a global shape recognition. And also we can have this tactile data for pose estimation. So for example, here we have a buried hands equipped with tactile sensors as the fingertips. And then we can get the tactile data from each fingertip, these 3 fingertips. And then we can apply principal component analysis. So we can get these handcrafted features from PCA. So we can get these axes, and so we take these axes as the features of this tactile data. So using these axes, eigenbasis, we can predict the poses of the tactile object pose. So by matching the variance between tactile and point cloud patches, and then we can get to know the pose of the object in hand. So for the previous methods, we see how we use traditional handcrafted features for predicting the shape and pose of objects. But also we can use deep neural networks to have these features automatically learned by deep neural networks. Here is one of our most recent works using attention-based networks for tactile texture recognition. So here we have the tactile synthesis as the input of the networks. And then we use the convolutional neural networks to extract the spatial features from the input. And for each feature from the convolutional neural network, we use one spatial attention module to attend the obvious features. So the main reason why we propose this attention-based mechanism is also from our human tactile sense. So when we manipulate objects, for example, when we play Lego blocks, so usually we will observe these edges or these extrusions compared to the flat surfaces. We pay more attention to these edges, extrusions, and we can know, okay, how to manipulate these Legos. So it means we pay more attention to some specific areas. So here is an example. So we pay more attention to this part because this part is in contact with objects, and also it has more obvious textures. So after having the spatial attention, and we can also have temporal attentions to compare these features from different tactile images in one sentence. And then we can pay more attention to one frame of this sequence. And then we can predict the texture label of the fabric. So this is done by one of my PhD students, Guanjun Cao, and he will talk more about this work later in the lightning presentation. So now we have seen how we use this tactile sensing for tactile perception. Next, we will see how we make use of vision and tactile sensing together. So first, here is some examples of data collected from fabrics. So for fabrics, we can have camera images taken by digital cameras, and also we can have the data from GelSight. And then we can have these convolutional neural networks to learn features from this data. And then we maximize the covariance between the features from the multimodal pipelines. And then we can enhance the perception performance of the robot. And also we can have cross-modal perception. So like touching to see and seeing to feel. It's quite common for our daily life. We can see one object and we observe some features and we'll feel similar features when we touch them. So here's a work we have attempted to have cross-modal perception. So we have these tactile inputs and we generate the pseudo visual output. and also vice versa. So we use generative models to generate the pseudo data from another modality. So this can be useful for online communications. So for example, we have this video inputs and we can generate the pseudo tactile sense on the other hand of the internet. So here are some outputs from this work. You can see we generate some realistic data for vision and tactile sensing. And also, in addition to this passive interaction with objects, so for example, we collect data. We collect the data first and we process the data offline. But also, we can have online interactive perception by interacting with objects. So for example, here we have one object and we can take one picture and see the global features of this object. And so then we can filter, and as we interact with objects, we get tactile data. And we can filter the possible locations of contacts by comparing the tactile patch against the global map. And then we can localize the contact. So it's something like Visuo-Tactile SLAM. Because here we use Bayesian filtering to determine where we are touching on the objects. Here is some results we have got for localizing the contact in these objects. As we move on these objects, so we collect the tactile data and we compare the tactile data against the global image, and we can localize its contact. And also, especially in this spatial time, so we can't access our physical labs, so someone may think of how about doing these experiments or collecting this data in simulation. So it's quite common. Yeah, this I know. I will finish very soon. So we use this simulation for doing experiments in simulation. So it's quite common to use video sensors in simulation, but we lack tactile sensors in simulation. So here's one of our state-of-the-art research generating simulations of a GelSight in Gazebo. So here you can see on the top we have real images. The second line we have simulation results. So here is a video. So on the left we have the real experiment, and on the right we have the simulated environment in Gazebo. And we can get the real image and also the simulated output from the Gazebo. And for more details, you can check Daniel's website as well. And Daniel will give you more details in his lightning presentation. And to wrap up my talk, so we have make use of these high-resolution camera-based tactile sensors for perception tasks. And also we have created these simulated tactile sensors in Gazebo. And for the future, we will focus more on intelligent perception through interaction, so to have more dynamics in this process. Okay, thank you.
Great.
Thank you. Sorry, a little
we're 5 minutes over. So I guess what we'll do is we'll just stagger everything back by 5 minutes and say everybody has the same amount of time as they were allotted. There aren't many questions coming up. Somebody's asked you for a reference on the Merkel cells, the density of 14 by 14 per square centimeter. But you can put that into the chat.
Yep.
During the next talk.
Yeah, I think we can save some time. I can tap in the chat box to the questions, and we can move on.
Cool. Good. Okay, so I think it's Robert next, and it's over to you now to host this session.
Okay. Okay, so for the questions, I will answer the question in the chat box later, okay?